So the last Tuesday, we have discussed the convergence of power series, and we find that there exists so-called radius of convergence of a given power series, and so that the power series will converge for all the complex number g, which has distance from the origin less than the radius of convergence. Okay. So now we will consider functions defined by power series. All right. So now for a complex number, we know a power series is associated by a complex number Z0 called the center of the power series, and complex coefficients Cn for n greater than or equal to 0. All right, so we can define a complex function f of z on the open disk d of z0, okay, as f of z is equal to the power series for all z in the open disk with center z0 and radius rho, and where 1 over rho is actually the lim sup of the nth root of the x value of the nth coefficient. And we know this upper limit always exists, and which is greater than or equal to 0 and less than or equal to positive infinity. Okay. All right. Okay, and so we shall say that the complex function is given by a power series about the center, so about the point z equal to z0. Okay, and now in the next theorem, we will give the main property of function given by a power series. So if a complex function f of z is given by a power series about the point z equal to z0 with an ROC rho, okay? And we know how to compute rho, right? 1 over the rho is the upper limit of the nth root of the x value of the coefficients associated with the the power series. Okay. So smaller. Right. So if we have such a function, then f of z is analytic in the open region or in the open disk. D of z0 rho, and its derivative f prime z can also be given by a power series about the same point, z equal to z0, with the same ROC ZO, okay, which is obtained okay, by directly differentiating the terms. Right, so differentiating each terms of the series. Okay, so that we write down that so that its derivative actually is given by a series which is obtained by termwise differentiation of this power series. So the termwise differentiation here, n from 1 to infinity, okay, and it's n Cn z minus z0 and minus 1, okay, and this new power series has the same ROC as the original one. Okay, so so we have several points to prove. First of all, we will show that the termwise, the series obtained by termwise differentiation, which is this, and you can see this is a new power series, and we will show that this new power series, all right, has the same ROC as the original one. Okay, so that the new series converges absolutely for every z in this open disk. This is the first point. The second point is to show that this one is indeed equal to the derivative of the complex function of z. So you can see that the f of z is analytical. Okay. Okay. All right, so let's see the proof. Now we first know that the power series summation n from 1 to infinity n Cn z minus z0 and minus 1. Okay. So which is n from 0 to infinity n plus 1 Cn plus 1 z minus 0 nth power. Okay, so this is the after the reindexing. So we have the new power series, and this power series has the same ROC rho as the original power series. Summation from 0 to infinity, Cn z minus 0 nth power, right? Since, so this derived it. Now the lim sup. So to find the ROC of the new power series, we compute the upper limit, all right, of the nth root of the, so the nth root of the absolute value of the coefficient of the nth term. Okay, so now we have n plus 1 here and Cn plus 1 absolute value. So that is the upper limit of this one. Okay. All right, and now, as we have demonstrated in the last example in last Tuesday, all right, on last Tuesday, that we know that okay, so first of all, we will take n goes to infinity, the upper limit. So we use the exponential function, all right, so logarithm. Okay, the logarithm here. And the exponential function, as we know, it is a monotone increasing and continuous function. All right, so that the lim sup of the exponential function of this sequence becomes to the exponential of the lim sup, n goes to infinity. And the logarithm, the natural logarithm of this one is n, and the logarithm the answer is 1 over n, and logarithm and of so n plus 1 is positive number, n plus 1 times Cn plus 1. Okay, this one. Since exponential function is a monotone increasing continuous function on the real line. Okay. And by theorem, okay, so we employ a theorem, okay, in section 15.1. So that would be a very good property. So let's see that. 15.1.I. Okay, so I have developed several theorems related to about the lim sup. Okay, all right. So we have that one here. Okay, so now we have the exponential function. So they put here, and now we have lim sup, And there are two terms, okay? So it's 1 over limit n plus 1. This is one term. And n plus 1 over n plus 1 here. Okay. So return product logarithm product becomes to the summation of two logarithms. So we have that. Okay. Now exponential functions, and so we have lim sup. So now the sum of the lim sup equal to the lim sup of the sum becomes to the sum of lim sup. So this becomes to okay, we have that. And the sequence here, as you can see, if you look at this way, okay. Now, the numerator is the logarithm of n, and the denominator is the linear function of n. And as we know, that even though the natural logarithm is an increasing function, but the growth rate of the logarithm is much lower than the n. So we know that this ratio goes to 0. So it has limit, okay, as we know from there. And so this is the limit. Because the sequence has limit, and if the sequence has limit, then the limit is equal to the upper limit, also the lower limit. Okay, if you read the section 15.1, so now you have no n plus 1, and the n here, and plus the lim sup. And from here, we can write the lim sup here. So this is become 2. Okay. Here. Now this is 0. Okay. This is 0. Right. And if you like, you can use the L'Hopital rule, because that this goes to infinity and the numerator goes to infinity and the denominator goes to, the numerator and the denominator are going to infinity simultaneously. But so you can do the L'Hopital rule by differentiating numerator and the denominator. So you can see this is actually equal to 0. Okay, so this is exponential. This is 0. Lim sup, I'm sorry. Okay, and I deliver this one. This is a sequence converge to 1 as n goes to infinity. Okay, so we know that by a theorem. Let me see. Okay, so this one becomes to limit. N goes to infinity, n plus 1, and n, okay, this one, times lim sup goes to infinity, and okay, and this is from a theorem, I developed in, see here. Okay, so this is by theorem 15.1.h. Okay, so we have AN and the BN. All right, so we have two sequences, and the terms they multiply together. Okay, and for AN, it has limit. When it has limit, then the lim sup of the product AN and BN is equal to the limit of the AN times the lim sup of BN. Okay, so that is from theorem 15.1.h. Okay, so I encourage you to read the several theorems I worked out for you to use when you doing the manipulation of lim sups. Okay. Okay, so we have that, and this is going to 1. Okay, so this is going to 1, and so we have the lim sup of n goes to infinity, and n plus 1, and limit Cn plus 1 here. Okay. All right, and this one, so this is the exponential function of the lim sup, and goes to infinity. All right, and so we have the logarithm of n plus 1 square of Cn plus 1. Okay. Okay, and again, so this is the lim sup. All right, lim sup. Okay, so you can see this is actually is equal to the alpha here. Okay, and alpha is going to equal to 1 over rho. Okay, so you can see. Any questions? So things limit n goes to infinity, n plus 1 is equal to 1. Okay. So this is equal to 1. Okay, and this again by theorem 15.1.I. All right, because exponential function is a mountain increasing continuous function. Okay. All right. All right. So the proof here to show this new power series has the same ROC with the original series is by applying several theorems we developed in section 15.1. Okay. Any questions? All right. So now we define g of z equal, so it is given by So this function, this complex function, okay, is defined for all z in the open disk with the center z sub 0 and radius rho. Okay. Now we will show that the original function f of z is analytical, which is differentiable at every point z in the open disk, and the derivative is equal to g of z defined here. Okay, so now we do that directly. Okay, so now fix a W in the open disk, and we choose R greater than 0 such that W minus 0, right? So the distance of the W from Z sub 0 is less than R, and R is less than rho. Okay. Okay. So now if Z is not equal to W, right, so we consider the quotient divided by here and the GW. Okay. All right, and so we now try to evaluate this difference. Okay, and we will show that if Z goes to W, and then this difference will go to 0. Okay. All right. So that's Cn. So we do the substitution. Okay, because that f of z, okay, is given by the power series. So that this is z minus z0 nth power minus w minus z0 nth power. And that for the denominator, we can subtract 1 and add 1. Right? So we have that. Okay. Right? And the minus summation n from 1 to infinity n Cn and w minus z0 and minus 1. Okay. Okay, so we have now when n equal to 0, we know that this is 1 minus 1. Okay, so this is 0. So the term is 0 already. All right, and so we just consider n from 1. Okay, because when n is 0, then the numerator is 0. Okay, for n equal to 0. All right, and so that we have Cn, okay, and z minus z0 nth power minus w minus z0 nth power divided by z minus z0 minus w minus z0, okay, minus n and w minus z0 and minus 1 is power. Okay. All right, and look at the numerator here. We know there is a formula an algebraic formula, the difference actually is equal to, they can be factorized in the following way. Okay, plus xn minus 2 y plus plus x squared yn minus 2 plus yn minus 1. Okay, so we know we have this. Okay, and so that xn minus yn divided by x minus y, we have n minus 1 plus x y okay, sorry, this is x. Okay, so x times y to the n minus 2's power. Okay, and so the quotient here, so that you can see that by taking x equal to z minus z0 and y taken to be w minus z0. Okay, so the ratio here give us this sum. Okay, so now we have summation n from 1 to infinity Cn of z minus z0's n minus 1's power plus z minus z0 n minus 2's power times w minus z0 plus plus z minus z0 times w minus z0 n minus 2's power plus w minus z0 n minus 1's power minus n w minus z0 n minus 1. Okay, so we have okay. Now we do the following arrangement. Okay, the arrangement is here. Z minus z0 n minus 1 minus z minus z minus z0 n minus 2 times w minus z0. Okay, because we subject, so that this time we will has 2. Okay, so we will have 2 z minus z0 minus 2 w minus z0 and minus z minus z0 minus 3 w minus z0 square. Okay, and we do something. Okay, so the final terms would be m plus 1. Okay, so you see here, this is equal to m plus 1 minus m plus 1 the minus z0 minus 1. Okay. So we have 2 here and m plus 1 that z minus z0 and W minus Z0 and minus 2 minus W minus Z0 and minus 1 square. Okay. So we actually minus something at something, okay? Okay. All right, and so we will have so for this term, we can have minus W minus Z0, okay? This term can be factorized this way. And again, this is Z minus Z0 minus 3 and W minus Z0. So we have Z minus Z0 minus W minus Z0 term, okay? It's here. And finally, okay, this one is equal to W minus Z0 minus 2, Z minus Z0 minus W minus Z0. Okay. So they have a common factor, which is just this difference. Okay. So we can take it out. Minus W minus Z0. Summation. All right. So N is from okay, and okay. Oh, and by the way, if n equal to 1, then we have only two terms, so they will cancel. Okay, so we start with the second term. Okay. Because when n equal to 1, so we take here, when n equal to 1, then the terms here, we have C1, and so we have 1, and equal to 0. Let's see. Oh, okay. Right. So starting here, 2, because when n equal to 1, okay. So here, when n equal to 1 here, so we have C1, and here is C minus Z0 minus W minus Z0 and Z minus Z0 minus W minus Z0 here minus 0's power 1 times Zero's power here. So this is C1, and the ratio is 1. 1 minus 1, so this is 0. Okay. So when n equal to 1, this term is 0. Okay. All right. So we start with n equal to 2. Okay. Yep. So starting with equal to 2 here. That's great. All right. So this 2 and to infinity and Cn. Okay. So we have z minus z0 n minus 2 plus 2, this 2 here, z minus z0 n minus 3 minus z0, okay, plus plus n minus 1, okay, n minus 1 and w minus z0 n minus 2. Okay, so we have, so now, and the difference is z minus z 0, z minus w. Okay, and summation n equal to 2 to the infinity and Cn, and the summation k from 1 to n minus 1, and k, okay, so this k from 1 to n minus 1, yes, and z minus z0, n minus k minus 1, and w minus z0, and k minus 1. Okay, so the difference after some algebraic manipulations, we end up with this formula here. All right. So that's okay. If z minus z0 is less than r, okay. Then we have that the summation. So we look at the here, the k from 1 to minus 1, and the k z minus z0 and minus k minus 1, and the w minus z0 k minus 1 factorial, and the absolute value of this sum is less than or equal to the summation of the absolute value of each term. Okay, so that is here z minus z0 and minus k minus 1, and here is w minus z0 and k minus 1. Okay, and we have assumed here that w minus 0 is less than r. Okay, and here we assume z minus z0 is also the absolute value is less than r. Okay, so that we have less than equal to summation k from 1 to n minus 1. Okay, and here is r2 to the n minus 2 power. Okay, so you can see this is r and r here. All right, and so this is constant. So we have and the summation. The summation is 1 plus 2 plus up to n minus 1. So we have to the n minus 1 times n. Okay, and r n minus 2. Okay, so the term here is that. Okay, so this is the estimate of this summation, of the size of this summation. All right, and so now, okay, oops, sorry. Now the absolute value of this difference, okay, will be less than or equal to z minus w, okay, because this difference is equal to this expression. All right, so the absolute value, all right, is less than, okay, equal to this summation times n infinity and Cn, okay, and the 2 and the R n minus 2. So the upper bound would be here. Okay, because the sum has magnitude less than or equal to this expression. Okay. All right, so we have this one. Okay, and we can replace this, we simplify this one. So this is equal to n squared and minus 2. All right, now since R is less than the ROC, okay, rho, so we have the nim sup. So we take a look at here. So look at this series sum. Now we take the nim sup, okay, of. So we use the root test, okay, n squared and Cn. Now, oh, by the way, maybe I together. Okay, I look at. So this is Cn and R n minus 2. Okay. Okay, so that this is the dim sup and goes to infinity. And so there are three terms, R n minus 2 times n square times, okay, So that the soup of this sequence there. Okay. So this is, we say this is AN, maybe it was BN and CN here. Okay. All right. So we are computing the upper limit of the product of the terms of three infinite sequence AN, BN, and CN. But we know that the lim sup of this one, okay, and this one is actually lim sup so the exponents are going to 1. Okay. So this sequence actually has a limit. Okay, so the limit goes to infinity. It's R. Okay, so this first. Second, maybe I just write here. This sequence has limit, so I just write the limit. Okay, so this sequence has limit, and this limit is equal to okay, and the second is that n log n also has limit. Okay, so the n root of n, we know this is equal to 1. As you know this in calculus, so this goes to 1. So the AN sequence goes to R, BN sequence has limit go to 1. Okay. So that by theorem 15.1 just like the theorem before, point H. So this is limit and goes to infinity R. This one limit. Okay, and lim sup. Lim sup here. Right, and so this is R times the square of 1 and times 1 over rho here. So this is R divided by rho, and this is this one, because we choose R less than rho, so the ratio is less than 1. Okay, so we see that the terms of this infinite series, okay, the terms by the root test, this is less than 1. So by root test, the sequence converge. So by root test, i.e. Theorem 15.1.0, okay, the infinite series to infinity n square Cn, all right, is finite. Okay, so it converges absolutely. Okay, so we see that this is a finite number. Okay, this is a finite number. Right. So that as z goes to w, we have fz minus fw divided by z minus w is equal to, so they goes to gw. Okay, right? Because when this is a finite sum, so this is a number, a positive number, and this you can see as z goes to 0, this goes to 0. Okay, so that the difference goes to 0. Okay, so this shows that so the quotient goes to G0 as z equals to W. Okay, so that f of z is differentiable. Okay, at z equal to W, and f prime z is equal to, and f prime w is equal to gw. Okay, so we conclude our proof here. Okay. Any questions? Okay. Okay. So even though the proof is lengthy, but it's very elementary here. Okay, so I will give you an elementary proof for this result. Okay. All right, so by repeatedly applying theorem 15.3.8, so we have here, right? So we start with okay. For all z defined in okay. All right, so we start with that one, and now so the first derivative becomes 2. All right, so this is the first derivative, as we have shown in this theorem. Okay. Now, because the first derivative is given by this power series, so that it is differentiable by theorem 15.3.8. So the second derivative becomes to be right, and the radius of convergence is the same, which is rho, as in the original power series. All right, so we can do it. All right. Okay. And so that the case derivative becomes to be n from k right to infinity, and n minus 1 up to n minus k plus 1, Cn z minus z0 n minus k for all z in the open disk here. Okay. For all k. So this is now in particular, if we evaluate the case derivative when z equal to z0, okay, then fk z sub 0. fk z sub 0, so you see that when n is greater than k, then the terms are zeros. So only n equal to k, so when n equal to k, this is constant. So we have n minus 1 up to n minus k plus 1. Okay, so n is okay, right? K, so we have k, k minus 1 up to 2, 1, and ck. Okay. So this is k factorial times ck. So this is implies that the coefficient, the nth case coefficient of the original power series is equal to this ratio. Okay. So actually, the case coefficients, the coefficients of the case term c sub k, is actually the case derivative of the power series function evaluated at z equal to z0 at the center of the power series divided by the k factorial. Okay, so that fz can be expressed from 0 to infinity, and f to the nth power z0 divided by n factorial, and z minus z0 nth power for all z in the open disk. Okay, so which is called the Taylor series expansion of f of z about the point z equal to z0. Okay. All right. Theorem 15.3.1, theorems 15.3.2 and 15.3.3 in the textbook. Direct consequences of theorem 15.3.a. Okay. So please see the textbook. Okay. So I will not set them express this right now to save the time. Okay. But I would like to show the result. Okay. Theorem 15.3.4, so-called termwise integration all right, the power series. Okay, in theorem 15.3.a, we know that when we do the derivative of a function given by a power series, okay, it's also given by a power series with the same ROC of the original power series, right? How about the termwise integration? So that the power series then from 0 to infinity c sub n, n plus 1, z minus z0, n plus 1, obtained. Because when we do the termwise, the nth term, right? If we do the termwise integration, right, so the nth term, when we do the integration of the nth terms, we know this is actually Cn n plus 1. Okay? Plus a constant, of course, but we just look at this term. Okay. So when we do the termwise integration, right, then we obtain a new power series here. Okay, so you see this is a new power series, okay, obtained by termwise integration of the original power series okay. So now the new power series okay has the same ROC as the original power series. Okay. So to prove this theorem, we compute the ROC of the new power series, right? So the proof here. All right, now since the new power series okay, which is equal to n minus n1 to infinity Cn minus 1 and n z minus z 0 n's power. Okay. So the coefficient of the nth term is c, so n minus 1 divided by n for all n greater than or equal to 1. Okay. So we now compute lim sup n goes to infinity Cn minus 1 divided by n here. Okay, so this is a little bit complicated, right? Now we actually apply the same techniques. So we use exponential function. So this is the exponential function of the natural logarithm. Here. Okay, and so that this is exponential function of the lim sup okay, since the exponential function is monotone, increasing, continuous function. Continuous on. Okay. So by theorem, 15.1.I, okay. So we have this one. Okay, and so we can deal with this lim sup. Now the lim sup, this one, okay, it's the lim sup. Okay, so that we have n here and represent Cn minus 1. Okay, and minus log n here. Okay? All right. Okay, so the lim sup okay, so that's n minus 1 divided by n times n minus 1 and the limit Cn minus 1. Okay, this term. Okay, minus lim sup divided by n here. But we know this sequence. We know that it has limit divided by n. This is equal to 0. Okay. So log n divided by n here. This it has limit. Okay. Not only upper limit. This is it's a convergent sequence and goes to 0. So this is goes to 0, and the ratio goes to 1. Okay. So that this is equal to 0 here. So this is implies that lim sup equal to 0. Okay. And we have an here times bn here. But we know the limit n minus 1 n. Okay, this ratio has limit, right? This is equal to 1. Okay, so this is limit n goes to infinity. Okay, times lim sup okay. This is by theorem 15.1.h. Right? So we use that property several times. Okay, so that the lim sup n goes to infinity log n Cn minus 1 divided by n here. This is equal to the lim sup n goes to infinity n minus 1 log reason Cn minus 1. So this is the lim sup log reason here. Okay, so we plug in back so that lim sup n goes to infinity and okay, this one is going to equal to exponential function of the lim sup okay, and so this is the lim sup exponential function of, so this is the lim sup okay. Okay, so they have the same terms. So this is 1 over rho. Okay. So even termwise integration give us a new power series, then this new power series has the same radius of convergence with the original power series. Okay. Any questions? All right, now, so in the previous section, we proved that any function given by a power series in analytic. Okay, and this section will show that any analytic function has power series expansion representation. Okay, so now, so we let f of z be an analytic function in an open set omega in the complex plane. Now assume that d sub 0 r with r greater than 0 be an open disk contained in omega. Okay. So that if, for example, right, so this is omega with an open set in the complex plane. And suppose we have an open disk with a center z0 here. So we try, so there must exist a neighborhood, right? Z0, and so there's open, so we can give right, an open disk such that the open disk, the R is as large as possible. Okay, but anyway, there is always find an open disk with center Z0, which is contained in omega, right? Because omega is an open set. Okay, so that we can always find an open disk, okay, inside here. All right, and that's so we let epsilon greater than 0 such that epsilon is less than r. Okay. right? And then, so the curls, the disk, with the center Z0, but so the bar, okay, but radius R minus epsilon. Okay, so we find an epsilon. So this is R minus epsilon here. And here, this is epsilon. This is R minus epsilon. So the curved disk, which means that the disk including the boundary, is contained in the open disk with radius R, with radius R, yes. Okay, here. Okay, so now f of z is analytic in the convex open set D0 R. Okay, so the open disk with radius R is a convex open set. Okay. And because F is analytic, in the open set omega, so that the same compass function is analytic in the compass open disk here. And this compass open set, which is simply connect, so it's a simply connected domain. Okay. Okay. So the green open disk is a simply connected domain. Now we let gamma prime be the boundary, circle of the crossed disk d bar z0 with radius minus epsilon. So that the real of the boundary is the gamma prime star. Okay, gamma prime star. And we orient it counterclockwise. So this is oriented here. So gamma prime is the boundary circle. Okay. Oriented counterclockwise. Okay, so it is clear that gamma prime is a simple closed path in D0R, okay, in the simply connected domain here. All right, so now we can apply Cauchy's integral formula. All right, so by Cauchy integral formula, okay, we have f of z is equal to 1 over 2 pi I of, and the gamma prime f of w, and the w minus z and dw for every point z in z0 and r minus epsilon. Okay, so for every point inside this circle with radius r minus epsilon. Okay. Okay, so this is from the Cauchy's integral formula. We have. Right. So now we fix a point. All right, z in this open disk, z0 r minus epsilon. Okay, so we fix this one. Okay. Now, since z minus z0 divided by w minus z0 raised to the nth power, and we take the absolute value here. Okay. And when the w is taken on the reciprocal path on the circle. Okay, so now for all w in gamma prime star. Okay, so now so the distance, right? Because w is on the circle and z0 is the center of the circle, so the difference is actually equal to the radius, and so this is r minus epsilon here. Okay, and here the numerator is z minus z0 in general. Okay, and raised to the nth power. Okay, so this is true, and for all n greater or equal to 0. Okay, so we know that here. And we know that the summation n equal to 0 to infinity, that z minus z0 nth power divided by nth power, okay, is finite whenever that the z, the term, right? See the, okay, so if this ratio is less than 1, so if the ratio is less than 1, then the power series, the sum of power series is finite. Okay, right, so from here we know that. Okay, so the infinite series of functions of w the function of w okay, so the series function, this one is n from 0 to infinity, z minus z0 divided by w minus z0 n. Okay. Okay. So this is an infinite series of functions of w. Okay. Remember, we fixed a point z, right? So z is a fixed complex number in this open disk. See here, so z is fixed, and the z0 is also fixed, right? It's just the center. Okay. All right. So we see that only w, okay, is changed, and when w is in here, you see that in here, in the circle, so that so we have this one, and the infinite series functions, this infinite series function will converge. Okay, so but as we know, this must be true because when z is in here, all right, then the distance of z from the center of the disk, all right, is less than the radius. Okay, so when z is in this open disk, must be true. Okay, this must be true. Also that this infinite series converges. Okay, and so the infinite series of function of z of w here also converges. So that this one maybe I write here w, okay, converges to the function of w. Okay, because this is a power terms, right? So it's converged to the function which is 1 divided by 1 minus z minus z0 and the w minus z0 here. And so which is equal to w minus z0 and the w minus z. Okay. Okay. And the convergence is uniform. Okay, on gamma star, on the circle. Okay. By wire traced. Wire traces. M test. Okay, for convergence. Okay, right, and this is very similar to the wire trace, the M test for convergence in section 11.3. Okay, when we discussed the Fourier series expansion in chapter 11. And this theorem will be shown again in the 5th section of this chapter. Okay, but the technique will be similar. So I will use that here, so that because that every term is, as we know that for all the W. So W is in the okay. Okay. We restrict ourselves for W is on the unit on the circle with radius r minus epsilon. Okay. So that's in here. So this is W here. Yeah. W here. Okay. Okay, so this infinite series will converge okay, of functions because each term is a function of W. Okay, and the W is in the circle, so that the denominator number 0. Okay. Right. So this one goes converge to that. Okay. Now, since f of gamma prime t is a continuous function, on the parameter interval alpha beta of the closed path gamma prime. Okay, so that f gamma prime t is bounded right, so the absolute value, we take the absolute value. Okay, so this one is a continuous function of the path space, so that this function is bounded. Okay, on alpha beta by the extreme value theorem in calculus. I.e., there x and m greater than 0, such that f of w less than or equal to m for all w in gamma prime star. Okay, because any path is a curve and it's a continuous function from a parameter interval, and here we always assume the parameter interval is from alpha to beta. Okay, and parameter interval is a finite closed interval. So by the extreme value theorem, that the continuous function, because this continuous function has real values, because we take the absolute value here. Okay, so it is bounded. Okay, because it has a maximum value and the minimum value. Okay, by the extreme value theorem. Okay. Right, so which implies that f of w divided by w minus z0. Okay, this s value is less than or equal to m. And the w minus 0 is r minus epsilon, okay, for all w on the circle here. All right, so that's the infinite series of functions of W infinity z minus z0 nth power divided by W minus z0 nth power times f of W minus z0. Okay. Okay. This one converges to okay. So they converges to f of W divided by W minus Z. All right, uniformly. On gamma prime star. Okay. Okay. Look at here. Because that we have the bound, right? So that this term has the bound for all the W in here, and we know that every term, okay. So that the function, this function. So this is equal to and that the infinite series converge to that function. So this is to Z, right? And so this is f of W and W minus Z. Okay. Okay. So this infinite series converge to uniformly to this function. Okay. All right. This all the preparation. So that's for every Z in the open disk, all right, with center Z0 and the radius R minus epsilon. So for every Z inside the yellow circle, we have that f of Z. This is from the Cauchy's integral formula, gamma prime, and f of W divided by W minus Z, and the dW. Okay, but this one is their series sum. Okay, of this one. So this is FW and Z minus Z0 nth power divided by W minus Z0 n plus 1's power and the dW. Okay, now, because that the convergence, this one converge to, so that the series, we know this infinite series of function converges to this function uniformly, okay? So that we can exchange the order of integration and the infinite sum. Okay, so that this comes to be summation n from 0 to infinity and 1 to pi I here, gamma prime fw and the z minus z 0 n's power and divided by w minus z 0 n plus 1's power and the dW here. Okay. So the reason is that the series sum n's power converges to Fw and the W minus Z0 uniformly on W in gamma prime star. Okay, so this is the reason, and this is from theorem 15.5.3. Okay, so we will show that because this is it's about the uniform convergence. So in the fifth theorem, that we have this result. So we can exchange the order of integration and the infinite sum. All right. Now, in here, this term is independent of W. Okay, so that this becomes to be n equals 0 to infinity to pi I gamma prime, and this is f of W and the W minus Z0 and n plus 1 dW times z minus Z0 to the n's power. Okay, but what is that? What is that? What is what? So this is actually the derivative. Okay, so this is actually n equal to 0 to infinity, and the Cn z minus z0 n's power. Okay, and with okay, so where Cn is 1 over 2 pi I and gamma prime Fw W minus Z0 n plus 1's power dW. All right, and what is that? This is equal to the n factorial of the n's derivative of the complex function z at Z0. Okay, so this is by theorem 14.4.1. Okay, so we know that for every Z in this open disk, the complex function has, you can see, has power series expansion expression here. And the coefficient Cn, it can be obtained by using the nth derivative of the analytic function f at z0 divided by n factorial. Okay. Right. Now we let epsilon go to, so by letting epsilon go to 0. Okay. So we have the following theorem. Okay, so when epsilon goes to 0, because epsilon, we choose epsilon arbitrarily, right? So when epsilon goes to 0, then the disk will expand. Okay, go to what? Go to the green one. Okay, the green one. Okay, with radius r. Okay. All right. So we conclude the main theorem here. And analytic function f of z defined in an open set omega in the complex plane. All right, it's representable by a power series in omega. That is, to each open disk d of z0 or in the open set, there corresponds a power series expansion of f of z about z equal to z0, and in this case fz is equal to this power series with coefficient, all right, the nth derivative of f at z equal to z0 divided by n factorial and z minus z0 to nth power. Okay, for all z in D. Okay, so we have this nice theorem here. Okay, so so you can select the open disk as with radius as big as possible, but still contained in omega. Okay, you can select omega as big as possible, and so the function has this series expansion. Okay, for all z in this one. Okay. So if you select different center, right, then the power series expansion will be different because the center will be different. Okay, but anyway, that well, it's just so that well, we can represent the complex function, the analytic function, by a power series locally. Okay, at least in a disk, all right, in omega there. Okay, so that it's possible because if we select different center, then So, for example, if you have a Z0 here, and you have another, say, Z1 here, okay? And so in the intersection for any Z, in intersection of these two open disks, so maybe this is R0, this is R1, and for here, f of Z is represented by right? So this, and for in here, okay, but in here we have all right. All right. So in this open disk, we have this positive representation. But in this open disk, we have another positive representation because they have the different centers here. So if Z is in the intersection, then Z has two. It has two different positive expansion. Okay. All right. So the representation of a point at a point may not be unique. It depends on the open disk you select. Okay? All right, so I'll stop here. Okay.